Alright guys, welcome back to the second set of videos. So basically, you should have already keyed in your results from your experiments of the flipping coin back into the Excel sheet link that's been given in this assignment. Okay, if not, we'll just continue from this part of the lesson. Okay, in this part of the lesson, if you take a look at your notes, so you'll realize that we are actually going to skip this portion of the notes on page 10. So right now, I'm going to focus on 18.3 and onwards. So just make sure that you are looking at the correct section of the notes. This is on page 10. Okay, so I repeat, we are not going to go through the part that has a star on it. We'll go through it during Google Meet. 16.3 we'll go through in this video itself. Alright, coming back to the video. Now, in this part of the video, right, we are going to explore two different concepts. Number one, what exactly is called a test cross. Okay, this test cross, right, is a technique that we use to help us identify an unknown phenotype. Secondly, we're also going to look at how we can describe sex determination in humans itself. And last but not least, there's an additional one that I want to add on today, which is how to interpret family tree, okay, or what I call a pedigree. Okay, I'll share a bit more about this thing towards the end of this entire video. First and foremost, just some true and false questions to get you started. Okay, if you look at all these questions, alright, actually they are also reflected in the assignment that you need to do online. So I won't go through too much in details, but basically I'll give you some hints as we go along. When a purebred tall pea plant is crossed with a purebred short pea plant, all the F1 generations will be tall. You're looking at purebred tall pea plant. So if it's purebred, you're looking at homozygous. Okay, purebred, you're looking at homozygous. Okay, to make this question easier, I'm going to give you a bit of hint. The tall allele is big T. Short allele is small t. Okay, I leave it up to you to go and complete whether it's true or false. Okay, so heterozygous, I hope you understand what is heterozygous. Basically, they have different kind of combination of alleles, and I think that should be what you need to take note of. Okay, if not, we'll move on to the actual lesson itself. Alright, so when an organism displays the recessive trait, right, you realize that they must always be homozygous recessive, which means that only when it's homozygous recessive, then the phenotype of the recessive trait will come out. But whenever there's a dominant trait, okay, when you're observing a dominant trait, you wouldn't know whether the organism is actually heterozygous or homozygous. Right, for instance, big A, small a, or big A, both will give you the same phenotype they are looking at. So this way, you actually cannot tell whether is it heterozygous or homozygous. So how can we prove the identity of the organism, whether is it heterozygous or homozygous? In this case, when they're showing a dominant trait, we should use something that we call a test cross. Now, a test cross, right, is actually a breeding experiment that we can do on organisms like the plants or the rats, so on and so forth. So we can actually use the breeding experiment to find out whether that organism is actually homozygous dominant or heterozygous. Okay, and all test cross, take note, all test cross, you need to cross, that means you need to mate that unknown organism with an organism that must have homozygous recessive genotype. So let me give you an example. Homozygous recessive genotype could mean small a. But this unknown organism that is over here, the unknown one that I'm not sure, can either be big A, or big A, small a. And I'm trying to prove by crossing this organism with a homozygous recessive genotype. So this is the one that you're not sure about. Okay, but this one you must make sure that it's a homozygous recessive genotype. So what can the cross result in? Basically, by looking at how the offsprings are like, right, you can actually tell whether the original parent, is it homozygous or is it heterozygous. Let me give you an example. In scenario 1, if the organism was homozygous dominant, all the offsprings are going to have the dominant trait, and all of them are going to be heterozygous dominant. Why? Okay, this diagram, right, that you see over here has to be filled up into your notes. Let's give us a bit of a breakdown of what's going on. Basically, what I'm trying to say is that if this organism, the unknown one, okay, the unknown one, if it is homozygous dominant, okay, because in test cross, right, means that you always cross with a homozygous recessive. That means you can only cross this unknown one with a homozygous recessive one, and you realize that this is what you end up with. If the parent is big T for the unknown one, and since the small t is the one that you can control, right, this is the known one. Okay, when you cross it out, you realize that this parent can only produce the big T allele, or the big T gamete. This one can only produce the small t gamete, right? And whenever, regardless of how the random fertilization works, 1, 3, 1, 4, 2, 3, 2, 4, right, regardless of how it works, all the offsprings here will end up with big T, small t. And therefore, all the offsprings will show the dominant trait. Now this is how we use to determine what exactly is the original organism. So what I'm trying to say is that if today you conduct a test cross, okay, and all the offsprings are tall in this case, it shows that the unknown parent is homozygous dominant. Okay, why? Because in test cross, I always go and purposely use a homozygous recessive one to go and cross with the unknown organism, and therefore I can work out in this manner. Let's take a look at the second scenario that could have happened. The second scenario that can happen, right, is if the organism is actually heterozygous dominant. So we are looking at like maybe it's big T, small t. What would be the case? If the parent is big T, small t, in test cross you always cross with a small t, right? So if you found the gamete, you realize that this can be big T or small t. This one will always be small t in this case. And if through the random fertilization, what happens is that you end up with big T, small t in this case, T, small t in this case, small t in this case, small t in this case. Now through this entire genetic diagram, you realize that if I look at the offspring itself, right, if I compare them, this is actually tall, short, and tall. Therefore, the ratio between them, right, is actually, if I compare a tall to short ratio, it's actually a ratio of 1:1. So this means that if this test cross were to happen, half of the offspring, exactly half of them, will show the dominant trait. The other half is going to show the recessive trait. Okay, so this is what you have observed if the offspring, the unknown one at the start, the organism at the start is actually heterozygous dominant, right? So now you see the power of a test cross, because with a test cross, right, you can actually prove the genotype of the organism that you're not sure of. But just know that in all test cross, you must always cross with a homozygous recessive organism. So basically, you cannot just randomly cross the organism. You must make sure that one of them must be homozygous recessive. The other one is that one that you are not very sure about. Okay, and this is how you can actually use test cross to help yourself understand what's going on. Next, we move on to this concept called sex determination. Now, in sex determination, we are very interested in this thing called the sex chromosomes. Now, your sex chromosomes are chromosomes that will determine the sex of an organism. Okay, there are two types of sex chromosomes, mainly X and Y chromosomes. Cells that produce gametes are what we call sex cells. Alright, so they actually produce gametes, and if you recall from your gametes, right, they're all what we call haploid. So they have the half the usual number of chromosomes. The other cells in your body are called the somatic cells. These are just all the other cells. These other cells, right, are having a diploid number of chromosomes, which means the original actual number of chromosomes. For humans, that's 46 lah. Okay, so for humans, 46 chromosomes are found in all the somatic cells, but the gametes, right, the gametes are what we call the sex cells, right, so they are haploid, which means that they are only having half of this entire number, which is 23 lah. Okay, so for humans actually have 22 pairs of non-sex chromosomes and one pair of what I call sex chromosomes. Therefore, this one pair, right, can either be XY or XX. So in the event that this individual, right, this person, when the parents conceive the child, the gametes that fuse together actually carry the X chromosome, and the other one also carry the X chromosome, then the offspring will be XX, right? In the case that's XX, you get a female as a kid. In the case that's XY, you get a male as a kid. Okay, so likewise, for all the males in the world, human males in the world, right, they also have XY chromosomes in their body only. They don't have XX. So if you think about it for a second, right, if the dad is an XY combination and the mom is an XX combination, okay, in this case there's no dominant or recessive, so both is capital letter. So if the dad is XY, the mom is XX, it means that when they form the gametes, right, from their original body, right, the mom can only form gametes that have the X chromosomes, won't have the Y. The dad, however, can form gametes with X or the Y chromosome, right? So based on these things, right, you actually can tell that during random fertilization, okay, if you have this combination, you get Ni with XX, and if you have this combination, you also get Ni with XX. But if you have this combination, you get Ni with XY, and if you have this combination, you actually Ni with XY. So this actually tells you that, right, actually to have a son or to have a daughter, right, it's actually just a 50-50% chance. Okay, so this is the case for human. It shows you that actually for humans, right, the male will all have XY chromosomes, the female will all have XX. So what I'm showing you on the right side, this is an image of all the chromosomes inside the usual cell in a particular person. And you realize that the X chromosomes, right, there's 2 of them, right? And there's no Y chromosome over here. So if there's no Y chromosome, this shows that this entire diagram came from a female. Okay, for a male, the image will show very differently. There will only be one of the X chromosome, and there'll be another one on the Y side. Okay, so these are what we use to determine for sex in humans. So the male gametes will either contain the X chromosome or the Y chromosome, whereas the female gamete, in the case of human, right, will only contains the X chromosome. So depending on how you determine which sperm actually fertilizes the ovum, right, you can actually determine the sex of the zygote. Then that's how the doctors actually determine whether the child is a boy or a girl. Okay. We're going to take a look at a short video to understand about this entire process of inheritance of gametes containing the X chromosomes or Y chromosomes.
My wife is pregnant right now with our first child, and when people see her with her big baby bump, the first question people ask, almost without fail, is it a boy or is it a girl? Now, there's some assumptions behind that question that we take for granted because of our familiarity with our own human biology. For human babies, we take it for granted that there's a 50-50 chance of either answer, boy or girl. But why is it that way? Well, the answer depends on the sex determination system that has evolved for our species. You see, for most mammals, the sex of a baby is determined genetically with the XY chromosome system. Mammals have a pair of sex chromosomes, one passed down from mom and one from dad. A pair of X's gives us a girl, and an X and a Y together gives us a boy. Since females only have X's to pass on in their egg cells, and males can give either an X or a Y in their sperm cells, the sex is determined by the father, and the chance of producing a male or a female is 50-50. This system has worked well for mammals.
Alright, so as you can see from the video itself, right, this shows that actually there's an equal chance that the offspring could be either a male or female. So whatever you have heard in the past, right, about all these traditional myths or not, like if you eat durian, you can end up with a son, or you see more male babies photos, then you end up with having a son, whatnot. It's all rubbish, okay? It doesn't make sense, not scientifically proven. So actually, when the sperm and the ovum actually fuses together, right, during that moment, when they form the zygote, it's already decided whether there's an X chromosome or Y chromosome that is found within the entire zygote itself. Okay, so either it's an XX combination or XY combination. So it's always 50-50. There's nothing saying that it's better to have guys or better to have girls or whatnot. Alright, and with that, we have actually come to the end of what I really wanted to cover in your notes. But right now, right, if you have a piece of foolscap paper, I'll strongly encourage you to go through the next few slides. Actually, it's only 2 slides. So I'll go through with you how exactly do you interpret diagrams like this, so at least it can help you when you do the assignment. Alright, so what we have over here right now is what I call a family tree or pedigree. Basically, it shows you how the entire family tree structure looks like. So this part of the lesson, right, these last 2 slides that I want to talk about, actually, if you have a piece of foolscap or blank paper with you to write down, it'll be good. Okay, but basically I want to teach you how to interpret such a family tree diagram to know what's going on. So when you first read this question, right, you realize that it's talking about a disease that's actually an inherited disorder. That means it gets passed down from generation to generation. And this is actually caused by a dominant allele, big H. Now, what do I mean by a dominant allele, big H? Because like what I mentioned previously, right, I don't want you all to go away with this idea that dominant means it's better. Yeah, I emphasize a lot of times that dominant doesn't always mean that it's a better allele. Okay, so dominant does not mean better. In fact, dominant just means that regardless of whether it's homozygous or heterozygous, as long as you have this allele, right, you'll be able to show the phenotype itself. So that's the meaning of dominant. Okay, just take note. Now in this question, right, if you realize that in this entire diagram, usually the boxes that's been shaded or the circles that's been shaded, right, shows individuals with the disease. So let's take a while to see what exactly can we infer from this legend. Basically, right, individual that does not have the disease, okay, that not having the disease in this case, in this question, means that they're actually homozygous recessive. Why? Because to have the disease, right, you must have a dominant allele, which is big H. So this helps to determine what's going on. If you have the disease, it means that you're either big H, that means homozygous dominant, or big H, small h, which means that you're heterozygous. This will help to determine whether you have the disease or you don't have the disease. So this question is actually asking you to find out about R and S. Now, individual R and S, right? Okay, please don't be confused. I shaded them in green because they're actually unknown. You don't really know what's their genotype, so you want to find out what's their genotype. But other than that, everything else in this entire diagram, right, you can actually give a bit of information based on your legend. So first and foremost, individuals without the disease will be small h, which means that this person is small h, 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 homozygous recessive as usual, homozygous recessive, homozygous recessive. This helps us to tell whether or not we understand what the legend is trying to show. But the problem that we have now is that for all these people that are being shaded, we have no idea of telling whether they are homozygous dominant in terms of BH, or are they heterozygous. Okay, so this is where the question comes in to make it a bit more confusing. So basically, I want to look at this set of family tree. Okay, take a look at this part of the family tree. Look at it closely. Basically, it tells you that this person has small h, okay, and one of the offspring has small h. If you understand from the entire inheritance thing that we are talking about so far, right, it shows you that this mother actually passed down the small h to the daughter. Okay, but the daughter must also collect the other small h, and the other small h must come from the dad itself. So which means that the other small h that came here actually came from here. So this is where the other small h came about. That means this father here, right, actually has a small h within itself already in the genotype. Okay, so since everyone that has a disease must at least have one dominant allele, this dad must be heterozygous. This is how I infer. Okay, can you follow so far? Alright, and this actually shows that the dad over here is actually a heterozygous condition. That's why it's possible for him to pass down the allele to the daughter that has no issue at all, the small h allele. Okay, but we still don't know which one the individual R actually inherited. But I can tell for sure that individual R actually got from the mom, because the mom is homozygous recessive, right? Must have gotten the other small h from the mom. I'm just not sure whether this individual R actually received a big H from the dad or small h from the dad. So that's something for us to think about. Okay, so this is an unknown that we'll explore it on. Now when we come back to the other side of the family tree, this part, you take a look at this entire family tree. Both the parents are small h, and small h, which means that both the parents are homozygous recessive. This shows that the kid over here, no matter what's the case, will always inherit a small h from the parent. So S, right, this individual S is actually small h. That means individual S is responsible for passing down the small h allele. Okay, whenever they have a kid, right, between R and S, okay, it means that S will always pass down the small h allele. This shows that, right, all the child, okay, the one that's being shaded right now is actually having one small h allele because it came from the mom, much like what we explained about the starting part. But all these kids have the disease. That means all these kids must have a heterozygous genotype as well. Now looking at this entire setup, do you know what exactly is the genotype of individual R? Because this shows you that, right, individual R must be heterozygous. Why is that the case? Because individual R actually passed down the big H to this first child, but the small h to the second child. But he also passed down the big H to the third child, and the small h to the other child. Remember, each time when they have a kid, right, we go through the entire DNA diagram again. It's a random fertilization. You don't know which one is the one, but at least you can tell that R is actually heterozygous, whereas S is homozygous recessive. And that's how you use a pedigree to give you information. Let's take a look at another example. Okay, once again, what we have over here is a disease that's caused by the Huntington's disease again. Okay, and it shows you certain information as you can see over here. So like what I mentioned just now, this is caused by a dominant allele. So in this case, let's just give you an alphabet so that we make it easier when we go through the whole thing. Let's say that to have the Huntington's disease, right, you must have this big allele, big H allele. This shows that the individuals that suffer from the disease, right, are either big H or big H small h, either homozygous or heterozygous. But I know that whoever that doesn't have the disease must be homozygous recessive. This gives me a bit of information that this person here is a small h, homozygous recessive. This is homozygous recessive. This is homozygous recessive. Because that's based on my legend. I can give all this information. That's what I do when I interpret the entire thing. Now, how do I look at the other people with the disease? I must tell whether they are either big H or big H small h. So right now you can actually realize, right, if this parent here, Jess, small h, right, it means that whenever they have a child, Jess can only pass down the small h allele to the child through the gamete. That means this Mary and this Ian over here must have a small h within themselves. Okay, I hope you're following so far. And of course, from the John side, Since Mary and Ian has the illness, they must also have the dominant allele. That means John must have at least one dominant allele. Do take note that this doesn't mean that John has both sets of dominant allele, because you still cannot tell much information, because you wouldn't know whether John actually could also have BH small h or BH big H. Okay, you couldn't really tell, because it could be that just somehow, because unlucky, right, random fertilization, John's small h, the sperm that has a small h allele, right, never ever got to fertilize an egg. So it's always the sperm with the dominant BH alleles that got managed to dominate in each time when they have a child. So this is the reason why I say that for John, right, you cannot really tell whether is he fully dominant or is he heterozygous. Let's take a look at the other two individuals over here, Kelly and Mike. Okay, if Ruth and Sarah both have this combination, I can tell that Kelly must also be heterozygous. Now, why am I so certain about this one? Because I can tell for sure that Ian, okay, which I did trace out from the top, Ian must have one recessive allele from the mom, must have inherited one recessive allele from the mom, and the dominant one came from the dad. So Ian must be heterozygous, which means that Ruth and Sarah, right, if you think about it for a second, Ian must also have passed down a recessive allele. That's why Ruth can get two recessive allele, and the other one must actually came from Kelly. Okay, so likewise, and likewise. If you look at the last child over here, Mike has the disease, so he must have at least a big H. But how can I be certain that Mike actually has one big H and one small h, or two big H? I'll give you an example. If you look at Ian and Kelly, right, if I do the Punnett square for them, this is what will happen. Okay, this is the Punnett square for their when they have a kid. The kid can either be big H, big H, big H, small h, big H, small h, or small h, small h. Which means that out of all these possibility, Mike can either be somewhere within this combination, or this combination, or even this combination, which is the same lah. But I only know that Mike cannot be small h, small h. So same thing over here. I cannot conclude about Mike, but at least I know that he's either big H, or big H, small h. So we'll be using this a lot when we go through this entire practice questions for this particular lesson itself. You just take note of this thing, and hopefully it can guide you better when you do the questions. That's all. Thank you.